two particles are connected by a light, inextensible string passing over a smooth, fixed pulley. B lies on a rough surface and A hangs freely. The system is released from rest. We want to find the tension in the string and the acceleration of the system. If we consider particle A, its weight, 6g, will act downwards. The tension in the string acts upwards. For B, we have the weight, 4g, acting downwards, the normal reaction force, R, acting upwards, the tension pulling it to the right, and a frictional force, since we have a rough surface resisting the motion. Mu, we're told, is 0.4. The system will accelerate so that A moves downwards and B moves to the right. Since the object is moving, the friction must be limiting friction, which is mu times R. If we consider first object A, F equals ma for this will give 6g minus t, the resultant force, is equal to the mass times the acceleration. For object B, the resultant force is T take away the friction, and this must be equal to its mass times the acceleration. We know the friction is 0.4 r, and r will be equal to 4g. Since the acceleration is horizontal, the vertical forces must be in equilibrium. So we get that T take away 0.4 times r, which is 4g, is equal to 4a, and tidying this, T take away 1.6g is equal to 4a. If we now add the two equations 1 and 2, we can see the tensions will cancel. 6g take away 1.6g gives 4.4g, and this will be equal to 6a plus 4a, which is 10a. So a is going to be 4.4 times 9.8 divided by 10, and this calculates to give us 4.312 meters per second squared. We now consider the equation T minus Fr is 4a. Together with the value of A we just calculated, we get the tension is 4a plus friction, which is 4 times 4.312 plus the frictional force of 1.6g, and this calculates to give us 32.928 newtons. We're now told that after 4 seconds the string breaks. We want to know the speed of particle A at this time. We can collect SUVAT information. We know the acceleration is 4.312 meters per second squared. We just calculated this. We know that the system starts from rest. We want v, and the time is 4 seconds. These four quantities are related by v is u plus at. So v is going to be 0 plus 4.312 times the time, which is 4, which gives us 17.248 meters per second. We're now told that B is 15 meters from the pulley when the string breaks. We want to know how fast it is going when it hits the pulley. If we now consider the object B moving along the horizontal surface in the time after the string breaks, there will be no tension force pulling the object to the right. The string has broken and therefore no longer pulls the object to the right. The only horizontal force acting then will be the friction, which we calculated to be 1.6 G. The friction will oppose the motion by producing a deceleration. If we now consider F equals ma, the resultant force on the object is the 1.6 G, and this must be equal to 4a. Which gives us that a is 3.92 meters per second squared in the direction shown on our diagram. If we now consider suvat for this object, we're told that it has 15 meters left to go before it hits the pulley. The speed will be the same as the speed of A after the string breaks, so 17.248 meters per second. We want the speed with which it hits the pulley, and the deceleration is 3.92 meters per second squared. These quantities are related by v squared is u squared plus 2as. This is equal to 17.248 squared plus 2 times minus 3.92 times the distance of 15. And calculating this, we get 179.89 and so on. V is then the square root of this, which is 13.4 meters per second, correct to 3 significant figures.